Good evening, my name is Jeremy Pate, and this is my MAE 170 final video. So I was tasked with taking a given plant and applying controllers and compensators to have it fall within some given parameters. Those parameters were a percent overshoot of less than 30%, a rise time of less than 0.15 seconds, a steady state error of less than 0.1, and a phase margin of greater than 60 degrees. So first of all, we were given a percent overshoot requirement. So from that, I could find a minimum zeta, which is the damping ratio for the system that would allow that requirement to be met. So that ends up being 0.317, or if you translate that into degrees on the real versus imaginary axis, it's 71.5 degrees from the negative real axis. So after that, I chose arbitrarily within that region a couple of complex conjugate dominant poles that I wanted the root locus to go through. And then next I plotted the G of S on the root locus, the uncompensated system, to see if I actually needed to add a compensator or if some value of K would bring me through those dominant poles. And unfortunately, since the original plant was had two complex conjugates on the right hand plane, it did not fulfill any of the system requirements. So I needed to shift the root locus over. To do that, I used a lead compensator. So first I chose a sigma z that was beneath my dominant pole. And then from there, I took the phase, and with the phase, you're able to find the sigma p. And with that sigma p, I took the magnitude and you're able to find the K value. So I had my first compensator. So I applied the lead compensator to see how it would modify my root locus. And the root locus did indeed go through my new dominant poles within 2 degrees. So that was a success. And then next I needed to apply a lag compensator because the steady state error had gone up to 0.97 and we are required to be below 0.1. So I took a lag compensator by initially setting omega times zeta divided by 50 as my sigma z. And then from there, I found my alpha, which is the desired steady state error over the current steady state error. And I multiplied the two to find sigma p. And that gave me my lag compensator. So brought my steady state error down within an acceptable range. And once I did that, the system was still unfortunately unstable, so I tried a couple different things. I did try to add a PID controller. Eventually, it kind of spiraled out of control and had an 8th order system. So I started over with a new zeta because the one I picked was 0.312, so it was a little bit small. So I thought that maybe a larger damping ratio would prevent the system from blowing up a little bit further down. So I did several iterations. I ended up, I think, 4 times I changed my zeta and went through the whole process. It took a little bit of time. I did unfortunately run out of time. I ended up settling on 0.6 as my zeta, but was not able to get the system to be stable, unfortunately. I did get some data though, and was able to get some of the system parameters, even though the system did not. It goes to infinity with the step response, which is not ideal, but the rise time is within the requirements. And same for the phase margin. Phase margin is 78.8, so that is above the 60 required. And then I did attempt to do a little bit of manual tuning on the compensators, but as you can see from the Nyquist diagram, we're actually pretty close here from this edge to 0. We are actually right around about 0.9. So unfortunately, the system is very sensitive. So the smallest tuning can cause it to spiral out of control, which is why I was not able to get this thing to actually
be stable.
But given a little more time, I would probably be able to add another uh, couple compensators, do a little more cascading, and get the correct values that would cause the system to be fully stable. Unfortunately, I did just run out of time, but thank you very much, and thanks for the class.